Hello. Some of you may wonder what NASA scientists do on their day off. Some of them climb Mount Everest, and some of them look at the transit of Venus, and some of them come to the Opera House in Malmo. So here I am today. That being said, for those of you who know me, don't be concerned. I will not be singing my talk today. I will be actually speaking it in real time. And what I'd like to talk about today is looking at biology as technology, designing solutions for Earth, Moon, and Mars. Now, I feel a little strange about the title because biology is, of course, the study of living organisms, and it's almost a no-no for an evolutionary biologist to use the word design in the same sentence, because design implies that there's a designer, that there's some sort of force behind that. And of course, as we know from my hero, Charles Darwin, that we don't talk about design in nature. There is no creator that is sort of micromanaging, as we say in the United States, quarterbacking evolution, that this happens in a way without any intent and purpose except to be able to survive and pass on your genes to the next generation. In fact, there was a paper a few years ago by Francois Jacob on evolution as tinker, and that, I think, is one of the most profound ways of thinking about nature, that evolution works with what it has. It's more like a designer or a creative professional, that you have what you have in your studio and you use it to make the next thing. You're not an engineer where you say the optimal octopus would have 8 legs and this and that and the other thing, because no designer would put the head and 8 legs and do all the things that an octopus does. But what if you could actually design nature? What if we could tweak what we have out there, or even better, what if we could actually make a cell from scratch? So we are able to do this sort of thing now. We're not actually make a functional cell from scratch, although I have colleagues who are extremely close to achieving this. But we are able to do an awful lot, and this is a field that we call synthetic biology. It's sort of an analogy to doing descriptive chemistry, and then we started doing synthetic chemistry 100-some years ago. And now we do not just descriptive biology, but synthetic biology as well. So what we're doing is talking about reprogramming organisms so that maybe they have a different morphology, or maybe a different metabolic pathway, or different set of genes, or whatever. Or, as I said, redesign them from nature. And the result is all sorts of benefits for mankind. We've used synthetic biology approaches to make new drugs. The poster child for this is an anti-malarial drug. We've done this to make biofuels. We've used this to make pharmaceuticals. We've used this for environmental remediation, for materials production, for food, and so on. Now, all this has been done for applications on the Earth up to now. And my point today is going to be there's no reason we shouldn't do the same things in our quest to settle the moon and ultimately Mars as well. So why should you do synthetic biology off-planet? Well, I sort of jokingly put in, well, it's my job, but I took that out, but the fact is it is my job. But it's also, I firmly believe, the only approach that's going to allow us to settle off-planet. Our ancestors, when they moved out of Africa, didn't bring all the things that they needed for the next 100,000 million years. They had to learn to live off the land. Our ancestors in the Americas, again, didn't bring with them everything they'd need for eternity, but rather they learned to live off the land. And we're going to have to do the same thing off-planet as well. But there's another point to this that I'd like to look at a little bit more closely, and that is that I believe firmly that by looking at using synthetic biology applications off-planet, that actually is going to help the applications on-planet. And there are a couple of reasons for this. And here I've just put together a sort of fun comparison of concerns with Earth, Moon, and Mars. But let's focus on that column on Earth for the moment. Of course, there are always going to be environmental concerns. You don't want to have little frankenbugs running around disrupting the ecosystem. And you also have to, of course, worry about human health. But here's a very important one that I think probably resonates with a lot of people in this room. They're economic concerns. If you find a really cool way to make cotton in a vat in a warehouse in, say, Malmo, you may be now disrupting the economics of Indonesia, and the Indonesian cotton farmers, therefore, may feel the economic pressure to do something else, or whatever sort of political ramifications there are there. Further, there are questions philosophically about tampering with life, and I'll get to that a little bit more at the very end. But those are concerns on the Earth, and therefore you have to move a little bit more slowly because you have to worry about all these downstream effects. Many of these go away when we start to talk about synthetic biology on the moon. There are no environmental effects that we need to worry about. No one's worried about zoning around such and such a crater. We have instead a huge problem with upmass, which I'll talk about again a little bit more later. There are no political concerns, there are no philosophical concerns on the moon. The moon is dead, it's always been dead, let's go for it. Mars is a little bit different. Well, I am repeating what's in the 1967 UN treaty here, so I'm on fairly firm ground here. Mars is a little different matter. The question is still open whether there is life on Mars or could have been in the past. And I think that there would be no greater tragedy as a scientist, and that's my other life as an evolutionary biologist, if there was an indigenous biosphere on Mars and we destroyed it, or we eliminated the possibility of ever discovering life 2.0. I mean, that would be an enormous scientific tragedy. So we do need to worry about actually protecting Mars from Earth-based life and vice versa in the remote chance there's something on Mars that would be infective on the Earth. Again, we have the upmass problem, which again we'll go into later, not the same sort of political problems. Philosophical, a few of my colleagues are concerned, well, what if there are Martians, even if it's at a microbial level, do we have the inherent right to go take over their planet? But we can leave those questions for another day. So that being all said, let me give you an idea of the sort of things we're talking about. And what I'm going to do is try to give you some proof of concepts that we've been doing in my lab. I've been the faculty advisor of a competitive synthetic biology group of undergraduates through the iGEM program, International Genetically Engineered Machine Competition. So I'll show you a couple of proofs of concept that these teams of students have done and other people in my lab. But let me go sort of more into this question of what it's like going forth from planet Earth. Now, what you see here is a picture that was taken from the surface of Mars. And I love to show this picture because it really gives you an idea how far away it is from the Earth. Can anyone see the Earth in this picture? Good. Let me help you out here. There's planet Earth, okay? It's a little tiny dot in the sky. And so I think somehow have in our imaginations that people on Mars are going to be micromanaged from the Earth. It's not going to happen. There's a time delay. It's this little tiny dot in the sky. And so what's going to happen with our descendants? Are they going to be up there and talk about Earth as something, oh yeah, you got to learn about it in school and take an exam before you go to uni? Or is it something, hey, if you want a really, really cool honeymoon, you could go spend 2 weeks on planet Earth? Or is it something that we're always going to be tethered to, and it's always very much linked? But in any case, there's going to have to be some physical separation because there simply is. And so here's some of the challenges that are going to be there for human settlement. And what's interesting is a lot of the things I'm going to talk about we currently solve on the Earth with petrochemical products. So the first thing is we're going to obviously need transportation to get there, and once we're there, we're going to want to move around. We're going to need habitats. We're going to need life support, and when I say life support, it's not even just the obvious things like food and medicine and so on, but once you're off planet, you have to worry about things like gravity. Mars has 1/3 of the Earth's gravity. You have to worry about oxygen. The whole atmosphere on Mars is only 7 millibars, so that's only 7% of what we have on the Earth. I mean, that's virtually nothing. Actually, it's less than 1%, I'm sorry. You have to worry about your clothing and recycling and so on. You need to generate power, you need to generate heat, you need to generate light, and certainly you need a lot of radiation protection because even though Mars is 1.5 times further from the sun than the Earth is, another half as far, it does not basically have an ozone shield to protect it from ultraviolet radiation. It doesn't have the magnetic field that we have on the Earth and so on. So radiation protection is a huge one. But our challenges to get to Mars, again, are not the same ones that we talked about for the Earth. And here's where I'm going to mention this upmass problem. It costs, and I'm sorry I can't do it in krona, but it costs about $10,000 to launch a can of Coca-Cola into low Earth orbit. And what do you have? You have a can of Coke in low Earth orbit. That's not going to get you a human settlement on Mars. It's going to cost that much more to go to Mars. And so upmass is where our cost is. It's not a matter of our quarterly report for our shareholders. It's not a matter of our client. I loved having that last talk be before mine, because we do literally have an eternity here to go out and settle the solar system. Well, 5 billion years, that's close enough. So anyway, what we do have to worry about is upmass. So where my colleagues may not care if a piece of equipment weighs, 500 kilograms, I do care a lot. I want that to be 5 grams. So what we're doing is driving innovation towards miniaturization. And along with that is the cost. So our cost is tied in with the mass. We also need to have good storage, we need to be flexible, and we need to be reliable, because you can't get to Mars and say, oops, I forgot something, I'll just call Amazon.com, because it just doesn't deliver on Mars, not yet. Now, what's interesting is that I've been hinting at the fact that if we use the conceit of doing synthetic biology for Mars rather than solving Earth problems, we get around some of these local political and economic issues. And so I firmly believe that means that we can do game-changing work that will ultimately feed back to solving problems on the Earth. So what's the big idea about using synthetic biology off-planet? And I have to say, I've been selling this program. I started this program about 10 or 12 years ago, and I've been selling it back and forth to Washington. And this slide really comes from presenting to a bunch of people on the NASA Advisory Committee with their white shirts and their pencil protectors. And I thought I'd given them this grand vision and that they would be blown away. And the chair of the committee looked at me and said, well, so what's the big idea? And I thought, whoa, I already did that. Okay, you take a deep breath and you say, okay, Star Trek. So what is the big idea? Well, we've been using biology to do chemistry off-planet for literally thousands of years. What do I mean? How many of you have had an alcoholic beverage or yogurt or cheese in the last, say, 24 hours, or maybe even the last few hours? That's biology doing chemistry for us. There's no reason we can't continue to use biology to do chemistry for us off-planet. We use organisms for material production on the Earth that we then turn into things like habitats. How many people here are wearing cotton or wool-based things, or leather in your shoes, or sitting there holding paper that's made out of cellulose from trees? We use biological products a lot for material production. Again, I don't see any reason we shouldn't do that off-planet. We send digital information to make actually biological material now, which is something that we didn't used to do at all. We've broken that physical link. So we can do that off-planet. We can send information and make stuff there. We use biology for nanotechnology. Everything in our bodies has to be very precisely controlled. So we're actually super nanotechnologists. Anyone who's still awake today, is not comatose, you're turning your chemical energy into electrical energy to run your body. And we could even make alternative biochemistry, so you have right-handed sugars in your body now and left-handed amino acids. Why not swap those? So here's an example of great biomaterials we use on the Earth. Here are the sheep with their wool and the trees with their wood and so on. But we're not going to take these sorts of organisms with us to Mars. Now, we're not taking sheep and silkworms and so on. But what we are going to do is take something like these. This is the baker's yeast that you use to make your bread or your beer in the West. And then we could use those. We can program those to make these sorts of materials, silk and wool and cellulose and latex and so on. So for example, a traditional way that we do habitats off-planet, like the Apollo missions, was to just bring the habitat with you and you live in a tin can. Our approach is to use something like biological calcite precipitation, or even fungal mycelia, the parts of fungi that are under the ground, this root-like structure that lives off of really literally garbage. And we've been able to take some of this mycelia, put it into molds, and start to make bricks, Let me give you an example of a brick that my students made this summer, and therefore move on to habitats. Others on the Earth are using this for imitation leather and other sorts of products. Metal extraction, we've done some proof of concepts where we've engineered organisms to very specifically bind metals from either used electronics or from the Martian or lunar basalts. If you want to know what sort of metals a human body can bind or use, take a look at the back of a vitamin bottle. And so here's an example, a cartoon of what we do, where we've got the metals attached to the flagellum of a bacterium. We've even played a little bit with making exploration platforms, like making a biodegradable drone, and look up biodegradable drone, that project went pretty viral, or a bio balloon. You could actually do this kind of thing. But design is very much specific to the environment you have, and so are organisms. So how are we going to take organisms into these very different environments? And for this, what I've suggested is we use biology to make a synthetic extremophile, an organism that can live at the extremes. And we've done this with a group of students. They call it the Health Cell Project. And here are these fun students to remind you that I really do have a team of great students behind me. So let me give you final thoughts. Biology is technology, designing solutions. Well, designing, should we do this sort of thing? And I would like to present to you the idea that we've actually been designing nature for literally 10,000 years or more. Everything you eat has been domesticated. None of you, I bet, have a pet wolf. Many of you may have pet dogs. You don't eat teosinte, you eat corn. So we have actually been designing nature for quite a while. But what I'm talking about is now going and doing it in a very surgical, precise, and actually, I would say, much safer way. And then we could talk about what actually is natural, but I think we'll leave that for another day. And with that, I thank you very much for your attention.